Oi, gente, bom dia. Estou eu aqui de novo. Hoje eu vou apresentar mais uma. Hoje temos atração internacional, a professora Rita Thomas, do Indian Institute of Information Technology, Cotton. Ela é uma pesquisadora, ela está no final do doutorado, ela trabalha com equações diferenciais não lineares, simetria de Lie e cálculo fracionário. A apresentação dela é intitulada A Comparative Study of Lie Symmetry Analysis and Invariant Subspace Method to Fractional Hunter-Saxton Equation. Agora eu vou falar em inglês porque eu estou muito chique. Hi, people. I know Rita brought some audience too. Hi, I'm Stefania. And now I have the pleasure to present Rita Thomas from Indian Institute of Information Technology, Cotton. She's a research scholar there. She studies different equations, Lie symmetry analysis, nonlinear differential equations. And now she will present a work with title A Comparative Study of Lie Symmetry Analysis and Invariant Subspace Method to Fractional Hunter-Saxton Equation. You can start, Rita. Thank you.
Thank you. I am Rita Thomas, research scholar at Indian Institute of Information Technology, Kottayam. My research area is invariant analysis and exact solution of nonlinear difference and differential equations under the guidance of Dr. T. Bhagiraj, Assistant Professor, IIIT Kottayam. Before moving into the presentation, I would like to thank the organizers of periodic seminar on fractional calculus. Now moving to the presentation. I'm going to talk about a comparative study of Lie symmetry analysis and invariant subspace method to fractional Hunter-Saxton equation. This is the outline of my presentation. In this talk, we discuss two analytical methods, Lie symmetry analysis and invariant subspace method, to found the exact solution of fractional Hunter-Saxton equation with a Riemann-Leibniz fractional derivative. And we give a comparative study of both techniques. First, moving to the introduction, we all know that fractional calculus is the generalization of integer order calculus, where it has many applications, like we can use it in the stress strain relation of viscoelastic material, anomalous diffusion equation. But the fractional derivatives does not obey the properties like Leibniz rule, chain rule, standard properties of integer order calculus. So to found an analytic technique to found the exact solution of fractional differential equation is a difficult task. Among such analytical technique, Lie symmetry analysis and invariant subspace method are the efficient tool to derive the exact solution of nonlinear fractional differential equation. Here I consider the fractional Hunter-Saxton equation, which describes the nematic liquid crystal behavior, and the equation is as in 2.1 dou t gamma zx plus zxx plus half zx square equal to 0, where the order 0 less than gamma less than 1 fractional order, and consider here the Riemann-Leibniz fractional derivative. Here the dependent variable z represent the splay wave propagation. We consider two analytical techniques, Lie symmetry analysis and invariant subspace method, to found the exact solution of this Hunter-Saxton equation, which Riemann-Leibniz fractional derivative. Moving into that, we just need some basic concept to understand the method to solve the fractional Hunter-Saxton equation. Riemann-Leibniz fractional differential operator is defined using the Riemann-Leibniz integral operator. As fractional calculus is the generalization of integer order calculus, we can define the integral operator, Riemann-Leibniz fractional integral operator, as the generalization of Cauchy nth order integral formula, where which is defined itn. If n is an integer, the Cauchy formula is itn equal to 1 by n minus 1 factorial integral t minus s power n minus 1 w of s ds, which is extended to, generalized to a real number. N is replaced by a real number when the factorial can be replaced by Euler gamma function, gamma of instead of n in Cauchy formula. If gamma in R plus, we can define the Riemann-Leibniz fractional integral operator as in 3.1. Using this integral operator, we can define the Riemann-Leibniz fractional differential operator as in dtn itn minus gamma. For this Hunter-Saxton equation, we restrict 0 less than gamma less than 1. So n is ceiling function gamma, which is 1. So we can uh, define for n equal to 1 for the Riemann-Leibniz fractional differential operator for this problem. And there are many differential operators like Caputo, Rees potential, fractional Laplacian, Etli Cobra there. So here I restrict my operators Riemann-Leibniz fractional differential operator. And I consider the techniques invariant subspace method and the symmetry analysis. First, we define and we consider the basics of invariant subspace method for partial differential equation, and we can generalize it to fractional case. In invariant subspace method, we consider first the invariant subspace. So an n-dimensional vector space Wn is invariant under the differential operator G if it satisfies the condition G of Wn subset of Wn. That is, for all W in Wn, G of W belongs to Wn. If that condition holds, then Wn is invariant under the differential operator. The basics of invariant subspace method for PDE is as in the following slides. Uh, Here we consider 3.3 is the partial differential equation dou W by dou T. Here the LHS is restricted to the time derivative, which is equal to Q of XW, Wx, dou R W by dou XR, which consists of space derivative of the dependent variable W only. That is in the RHS, a nonlinear operator Q is here, and the invariant subspace uh, method is introduced by Galactinov for PD, which is as here. First, consider the vector space Wn of dimension n, which consists of n linearly independent functions Hj, which can be obtained by solving the nth order linear ODE 3.5. But we don't know that if that Wn is a invariant subspace for this Q. For this nonlinear operator Q, we want an invariant subspace. So the invariant condition of Wn is L of Q of W equal to 0 whenever L of W equal to 0. That is, for this nonlinear operator Q, we want to found the invariant subspace, which is obtained by this invariant condition L of Q equal to 0 whenever L of W equal to 0. Solving this, we can obtain the constants Bn minus 1, Bn minus 2, B0. Substitute in 3.5. By solving that linear ODE, we can obtain the uh, invariant subspace Wn. That is, for this operator, we first obtain the invariant subspace. That subspace is used to found the exact solution of the PDE using this theorem, which states that let Wn be the vector space spanned by n linearly independent functions Hj, and if Wn is invariant under the nonlinear differential operator Q, then there existed functions Qj such that this equation 3.7 holds, where Qj are the expansion coefficient of Q on the basis of Hj. It follows that the PDE admits the solution 3.8, where the functions eta j satisfies the system of ODE. That is, in the previous slide we discussed, we found an invariant subspace Wn, and we can represent the solution of the PDE in the separable form 3.8, that is Wxt equal to summation j equal to 1 to n eta j hj of x. And we can found this eta j, then we can easily obtain the exact solution of the PDE. And eta j can be obtained by substituting this W to the original PDE. Eta j satisfies the system of ODE, and we can solve this and obtain the exact solution of the PDE. This is the concept introduced by Galactinov and Stravinsky. Uh, Next technique is Lie symmetry analysis for fractional differential equation. To understand that concept, we need some basic concept. Asymmetry analysis for differential equation is introduced by the Norwegian mathematician Sophus Lie, in which he used symmetries to solve the differential equation. He inspired from the concept of Galois theory, where the permutations of the roots of the polynomial be the discrete symmetries used by Galois. He considered the symmetries for differential equation, which is continuous symmetries. So he introduced Lie symmetry for differential equation, and we can use and extend that concept to fractional differential equation and obtain the exact solution. And we can move to some terms used to obtain the exact solution using Lie symmetry analysis. First one is one parameter D group of transformation. We first know what is that. For that, we first define one parameter group of transformation is defined as in this equation, that is, let x equal to x1, x2, etc., xn lies in a region D subset of Rn. Then the set of transformations. This transformation forms a one parameter group of transformation if these four condition holds. That is, x star is this transformation defined from D cross S to D, where S is a subset of R and D is a subset of Rn, and this epsilon lies in S and X lies in D. Corresponding to that, we can define the law of composition of parameters epsilon and delta as eta. This x star forms the one parameter group of transformation whenever for each epsilon in S, the transformations are 1, 1 and 1, 2. It's bijective. And S with the law of composition eta forms a group, that is closure, additive, inverse and identity will exist. And for each x in D, for epsilon equal to epsilon naught corresponds to an identity element, that if epsilon naught is 0, then x of x epsilon naught equal to x, the identity property. And if x star acts on x with the epsilon and x double star acts on x star with the parameter delta, then x double star equal to x of x eta epsilon delta. This is the one parameter group of transformation, which is a one parameter Lie group of transformation. In addition to that four properties, epsilon must be a continuous parameter, that is S is an interval, and x star is infinitely differential with respect to x and an analytic function of epsilon in S, and eta is an analytic function of epsilon and a delta. And the basic concept is, in the invariant subspace method, we use the invariant condition as L of Q equal to 0 whenever L of W equal to 0. Here we use the idea that an infinite differentiable function f is invariant function of the Lie group of transformation if and only if f of x star equal to f of x. This idea is extended to the differential equation case, and we can easily understand what is one parameter Lie group of transformation using this example. That is, group of translations in a plane can be represented as x star equal to x plus epsilon, this, and y star equal to y. In plane, this is the group of translations which eta is epsilon plus delta, which satisfies all the seven properties in the previous slides, which can be represented as the motions parallel to the x-axis. And at x naught, this is the curve represent the evolution that x star at x naught and epsilon. Uh, this is the one parameter Lie group transformation definition. We use this concept to uh, what is how to found the exact solution of Lie symmetry analysis of fractional PDE or PDE. For that, we need some more terms. Uh, we want to know some more terms to understand that concept. For that, we already discussed X star is a one parameter Lie group of transformation. And X star can be expanded using the Taylor's theorem. We can expand like this. And we omit the epsilon square terms. X star can be represented like this, x star plus epsilon psi x. So psi x is defined as dou x by dou epsilon at epsilon equal to 0. This transformation is the infinitesimal transformation, and psi i's are the infinitesimal, and we can define the infinitesimal generator as summation psi I dou xi. And here we define the operator as the commutator relation or bilinear bracket as x gamma x beta equal to x gamma x beta minus x beta x gamma. So for that, consider if x1 and x2, if x1 is dou by dou x and x2 is x dou by dou x, then x1 x2 is dou by dou x, x dou by dou x, which is dou by dou x minus x dou by dou x of 1 into dou by dou x, which is 0. So that can be x1 only. Similarly, we can extend to it any exercise. So a Lie algebra is a vector space over ROC with the bilinear bracket operation defined like this: x gamma x beta commutator relation satisfies these three properties, that is the skew symmetry, Jacobi identity, and the commutator of any two infinitesimal is another infinitesimal generator, that is x1 x2 x3 be the infinitesimal, then x1 x2 is x1 or x2 or x3 or the combination. We can define that concept to fractional PD, how to solve the fractional partial differential equation using Lie symmetry analysis. For that, consider the equation 3.18, which is a fractional PDE dou gamma dou T gamma of W equal to G of XW Wx dou R W by dou XR. Assume that this equation is invariant under the one parameter continuous infinitesimal transformation 3.90, where psi, tau, eta are the infinitesimal transformation corresponding to the variables x, t, and w. And we can extend it to higher dimension. For wx, it is eta 1. For wxx, it is eta 2. And eta t gamma for the fractional case be the extended set of infinitesimal, which and the derivation is in Bowman textbook as eta 1, eta 2, eta r are already defined like this, and the gamma extended infinitesimal is defined like 3.23. Using these infinitesimals, we can define the infinitesimal generator as psi dou by dou x, tau dou by dou t, plus eta dou by dou w and eta 1 dou by dou wx and eta r dou wr dou xr and eta t gamma and the corresponding fractional derivative term. This is the infinitesimal generator we defined, which is the extended infinitesimal generator. That is, we extend psi, tau, eta to the higher dimensional wx and this time fractional derivative time. Then the one parameter Lie group of transformation admitted by the fractional PD if and only if W gamma or G equal to 0 whenever G equal to 0. That is, G is the original fractional PD. Using this invariant infinitesimal criterion, we can obtain psi, tau, eta, and using that infinitesimal, we can obtain the exact solution of the fractional PD. This is the technique used in Lie symmetry analysis. And in invariant subspace method, we use the invariant condition and found the invariant subspace, substitute in the separable form to the original PD and obtain the exact solution. Uh, these are the basic concept of Lie symmetry and invariant subspace method, and we can use this technique to our problem. First one is we use the invariant subspace method to the fractional Hunter-Saxton equation. That is, a fractional Hunter-Saxton equation is dou t gamma zx plus zxx plus half zx square equal to 0. So we consider the fractional time derivative in the LHS and the other part in the RHS. That is the space derivative of the dependent variable in the RHS. So as in 4.1, we consider the fractional PDE where f is the nonlinear differential operator consists of the space derivative of the dependent variable only. And we first obtain the invariant subspace, which is denoted by V, which consists of linearly independent vectors v1, v2, vr. And vr is invariant under this operator if this condition holds. And we express the exact solution in a separable form as a1 of t, v1 of x plus etc. ar of t, vr of x. Substitute this solution to the original fractional PD, we can obtain the A of t's, and that A of t's satisfies the fractional ODE, and we can found that AX, and the VR is obtained by, as in the basic idea, VR is obtained using this invariant condition L of f equal to 0 whenever L of z equal to 0. But in the invariant subspace method, the maximal dimension of invariant subspace is defined as n less than or equal to 2r plus 1. That is, for a differential operator of order r, the maximal dimension of invariant subspace is less than or equal to 2r plus 1. Here, for fractional Hunter-Saxton equation, r n less than or equal to 2r plus 1. R is the order is 2. So n less than or equal to 2 into 2 plus 1, which is less than or equal to 5. And we want to found first the invariant subspace for the nonlinear operator f. For that, we consider this ODE where r less than or equal to 5. We first consider if r equal to 2, we can obtain the invariant subspace by putting L, this is L, and L of f of equal z equal to 0 whenever L of z equal to 0. Using that, we can obtain the constants for this ODE, and we can obtain the polynomial invariant subspace 1x. So in invariant subspace method, we consider the solution in the separable form. That is, z is in the form a1 of t plus a2 of t into x. We substitute this separable form solution to the original fractional Hunter-Saxton equation, and we can obtain this OD, fractional OD dot T gamma A2 of T equal to minus half A2 of T square. That is, our original PD is reduced to fractional ODE, where the fractional derivative is here, Riemann-Leibniz fractional derivative, and we can obtain the A2 of T like this. So the solution of equation 2.1, which is the fractional Hunter-Saxton equation, is equation 4.8, where g of t is an arbitrary function. That is, the solution of fractional HS equation is z equal to g of t minus a1 of t is represented as g of t. That is an arbitrary function, and we can obtain a2 of t like this and putting this x here. This is the exact solution using the two-dimensional invariant subspace 1x for fractional Hunter-Saxton equation. And if we put g of t equal to 0 and g of t equal to t by 2 plus 1, the two-dimensional and three-dimensional graphical representation for the solution is as in these figures. Next, we can consider r less than or equal to 5. So, for 3, 4, 5, for this particular equation, we can obtain the same solution as 4.8. The same solution is obtained because all other ai becomes 0. So, we can obtain same solution for this particular equation. And we can also consider a general case, which is, first we consider a1, a0. Instead of that, we can consider a1 of x and a0 of x. It is a variable coefficient, and we can found that variable coefficient also. Instead of found the constants, we can extend the concept to variable coefficient case. But here, that does not make any uh, major difference in the solution. We can obtain the two-dimensional invariant subspace as 1x minus c square, which is substitute to the original PDE. We can obtain this fractional ODE. Solving, we got the trivial f of t is the solution. So this is a particular case of the above solution. But many other equations, this variable coefficient will leads more solution. So this is an extended case of the invariant subspace method, but this equation, this does not make any more change in the solution. Next, we can explain the Lie symmetry analysis of fractional PDE to the Hunter-Saxton equation. For that case, we have the fractional PDE dot T gamma Zx equal to F, and consider this equation is invariant under this one parameter continuous infinitesimal transformation, and as in the previous slide, we can extend this infinitesimal transformation to eta x, eta gamma t, and eta gamma plus 1 xt. And in our paper, we already derived the formula for eta gamma plus 1 xt for differential difference equation. Similarly, we can obtain the expression for eta gamma plus 1 xt as 5.5. Using this expression, we can obtain the infinitesimal operator as psi dou by dou x, tau dou by dou t plus eta dou by dou z plus eta x dou zx. That is, these are the terms which are included in the fractional Hunter-Saxton equation, plus eta gamma plus 1 xt dou by dou of the time fractional term. And the infinitesimal criterion for the fractional Hunter-Saxton equation become V gamma plus 1 g equal to 0 whenever g equal to 0. That is, g is the original fractional HS equation. That is, here we apply, this is the illustration of the Lie symmetry algorithm. We have the fractional Hunter-Saxton equation. So 2.1, that is the HS equation, is invariant under the one parameter infinitesimal transformation, that is x star equal to x plus epsilon psi tau star t star equal to t plus epsilon tau, that transformation, which transform the original HS equation to 5.8, and we use the transformation to give the invariant equation as here. Instead of this, eta gamma x system of equations as in 5.10. Solving this overdetermined system of equation, the infinitesimal become psi equal to c1x plus c2, tau equal to c3t, eta equal to c1 minus gamma c3z. So these are the infinitesimal obtained using Lie symmetry algorithm. So the infinitesimal generator becomes psi dou by dou x plus tau dou by dou t plus eta dou by dou z. So putting psi, tau, eta values here, and the symmetry algebra is three-dimensional with the basis that is corresponding to this parameter c1, x dou by dou x plus my z dou by dou z, and corresponding to c2 dou by dou x corresponding to c3 t dou by dou t minus gamma z dou by dou z. These vi's and the commutator forms the commutator table as v1 v1, that is v1 v1 is as in the commutator relation we defined earlier, which forms 0, and v1 v2, that is x dou by dou x plus z dou by dou z dou by dou x minus dou by dou x of this one, which forms minus x2 minus v2, and we can similarly compute the commutator table, and corresponding to all vi's and the combination we can obtain the solution as, if we consider v1, which is x dou by dou x plus z dou by dou z. Corresponding to this, the characteristic equation is of the form dx by x equal to dt by 0 equal to dz by z. Solving this equation, we can obtain z as x into f of t, where substitute this to the original PDE, this f of t must satisfy the fractional ODE as 5.40, and solving this we can obtain the exact solution of fractional HS equation as 5.50. Similarly, using this V2 we can obtain the solution f of t, and V3 we can obtain the solution same as the 5.50, same solution can be obtained. And next interesting case is v1 plus v3 gives a similarity variable and the similarity transformation corresponding to that generator. That is, if v1 plus v3 is considered, we can obtain the solution of the form z equal to t power 1 minus gamma f of x t x by t. That is, x by t is the similarity variable and this is the similarity transformation. This similarity variable and similarity transformation reduces the fractional HS equation to a nonlinear fractional ordinary differential equation in terms of Edley-Cover fractional differential operator. That is, in the invariant subspace method, we can reduce the fractional PDE to fractional ODE, which consists the same differential operator. Riemann-Leibniz differential operator PDE reduces to Riemann-Leibniz fractional ODE. Here, in the case 2 and 3, V2 gives fractional PDE reduced to the Riemann-Leibniz fractional ODE. But here, using the similarity variable and the similarity transformation obtained using this generator reduces to the fractional PDE to fractional ODE involving Edley-Cover. Other than the Riemann-Leibniz derivative, we can obtain this 5.20, which is a fractional ODE. Solving this fractional ODE, we can obtain the solution like 5.21. That is z equal to same term as in the above vi's plus extra c1 plus t power 1 minus gamma. If we put c1 equal to 0, this solution coincide with the first case. Similarly, this is the basic definition of Edley-Cover fractional differential operator, which is defined using the Edley-Cover fractional integral operator K. This is the basic definition. Similar to the Riemann-Leibniz integral operator, using that we define Riemann-Leibniz fractional differential operator. Some differences is in the equation, but this is the another representation of fractional differential operator, which is Edley-Cover. uh, V3 minus V1. This infinitesimal generator also give a similarity variable and similarity transformation, which also reduces the fractional HSPDE to nonlinear fractional ODE in terms of Edley-Cover fractional differential operator. Solving this, we can obtain the solution 5.27. And if we put C1 equal to 0, we obtain the same solution as in the first V1 case. So these are the two methods which are used to solve the fractional Hunter-Saxton equation. But we can use these techniques to any PDE and we can obtain the solution wherever possible using these techniques. For HS equation, we can compare this method as in Lie symmetry analysis, we obtain the exact solution using the Lie point symmetries, and we use the generator and obtain the similarity variable and similarity transformation. Using that, we can convert the fractional PDE to fractional ODE involving Edley-Cover fractional differential operator. In invariant subspace method, here we have only polynomial type invariant subspace and we construct the exact solution using that polynomial invariant subspace. And in polynomial type invariant subspace case, we can obtain an arbitrary function g of t and we plot the graph for g of t equal to 0 and g of t equal to t by 2 plus 1. From the graph, it is clear that when gamma tends to 1, the solution approaches to the classical solution of Hunter-Saxton equation. That is, when we put gamma equal to 1, then the fractional PDE reduces to the integer order fractional Hunter-Saxton equation. So when we put gamma tends to 1, the solution also approaches to the integer order fractional Hunter-Saxton equation solution. The differences is in the invariant subspace method, we can reduce the fractional PDE to fractional ODE, which consists of Riemann-Leibniz derivative. And in the Lie symmetry, fractional PDE converted to fractional ODE using the similarity variable and similarity transformation, with the fractional derivative is Edley-Cover and Riemann-Leibniz. Both are occurred. And the solutions obtained in Lie symmetry analysis are the special case of the solutions of the invariant subspace method. That is, invariant subspace method, we can obtain g of t, which is a general function. So Lie symmetry analysis solutions are the special case of the exact solution obtained by using invariant subspace method. That is, in the invariant subspace method, we first found the invariant subspace and using the separable solution, we obtained the solution. But in the Lie symmetry analysis, we put a restriction, that is, eta is linear in Z and which is computationally very complicated in the Lie symmetry analysis. For this particular equation, invariant subspace method is computationally easy and efficient technique to found the exact solution compared to Lie symmetry analysis. Invariant subspace gives a general solution. Uh, Instead of fractional HS equation, we can use this techniques to fractional differential equation and fractional differential difference equation, and many type of fractional equations can be solve using these efficient techniques. And this is the selected references. And thank you. If you have any queries, please ask.
Rita, thank you.
Yes.
We have, I, let us see if we have any questions. We have a compliment here by Junior, by Felix. First, congratulations, excellent presentation. Now a question from Junior. A compliment too. Sorry, I'm nervous. uh, Rita, congratulations by your excellent presentation. We are very honored by your participation in the seminar on fractional calculus.
Thank you. Thank you so much.
Now, a question. The two methods you presented are forms of linearization of an FPDE or FODE. Which one do you conclude is the most promising in terms of finding solutions?
Actually, this is not the linearization of fractional PD or fractional OD. Here, we are considering uh, in the symmetry analysis and invariant subspace method, we use the invariant condition and reduce the fractional PD to fractional OD, and we use the fractional PD is nonlinear and the fractional ODE is also nonlinear, but PD is reduces to fractional ODE. That is the only difference, and the variable is different. By converting fractional PDE to fractional ODE, we use the similarity variable and a similarity transformation. That is why fractional PD reduces to fractional OD. That's not the linearization property. And for this fractional HS equation, invariant subspace method gives the general solution. That is, we obtained all the uh, we obtain exact solution using Lie symmetry analysis using many generators, which gives the solution which are only a particular case for the exact solution obtained by invariant subspace method. But for this equation, invariant subspace method gives the better solution or the general solution. But in general, for different equation, we can say some cases Lie symmetry gives a better solution. In some differential equation, invariant subspace method gives a better result. But the difficulties are in Lie symmetry analysis, we restrict eta is linear in the dependent variable, because for fractional calculus, chain rule and Leibniz rule, that non-standard properties exist. So difficulties of chain rule, we consider eta is linear in the dependent variable. That restriction is there. But in invariant subspace method, we don't put any restriction. But the if only an invariant subspace exists, then only we can found the exact solution using invariant subspace method. Both methods are efficient to solve fractional PDs, but both have uh, advantages and disadvantages. For this particular equation, invariant subspace method gives the general solution. That only we can say.
Okay, thank you. Now, Felix question. Is there a difference between subspaces when we use different fractional derivatives? For example, what happens if we use Caputo derivative?
Uh, if we use Caputo derivative, then only the change occur in the A of t. That is, we first found invariant subspace for the nonlinear operator which contain only derivative of space derivative terms occur in the nonlinear differential operator, and we obtain the invariant subspace. If we use any time fractional derivative here, that is Caputo, Riemann-Leibniz, fractional Laplacian, Riesz potential, Hilbert derivative, that only in the occur in the LHS. The if only consider the nonlinear operator consists of space derivative, if there no mm, fractional derivative occur, the same invariant subspace is obtained, and that invariant subspace, using that invariant subspace, we found the exact solution in the separable form, that is z equal to summation a of t hj of a hi of x, that is hi of x is the invariant subspace, that is same, and we want to find a of t, that a of t satisfies in Riemann-Leibniz if d gamma a1 equal to a1, in Caputo d c d a equal to a1 of t, that is different. So we obtain the a of t are different by using different Caputo fractional different fractional derivatives. So only the differences occur if we consider the time fractional is in the AI of t, obtaining the AI of t's. So that I can explain using simply I can explain if uh, Caputo derivative of a constant is 0, but Riemann-Leibniz derivative of t power 1 minus alpha equal to 0. So that difference will occur in the solution part if in the time fractional case is different, but generally we can say in the space derivative, non-linear space derivative time, if the Caputo fractional space derivative term occur, then the concept is much more difficult, because to found the invariant subspace for the nonlinear fractional differential operator is difficult, but we can obtain, because for Caputo fractional derivative of Mittag-Leffler function is Mittag-Leffler function. So for that nonlinear operator also we can found invariant subspace, and if we consider Riemann-Leibniz in the nonlinear, actually in the Caputo are used as the space derivative case. Riemann-Leibniz is more used in the time derivative portion. So that difference will occur if we consider time derivative in the LHS, which is different, which only affect the A of t. If the fractional terms occur in the nonlinear space derivative terms, which affect only the invariant subspaces case. And you can also verify my paper for fractional differential difference equation, which is similar to differential equation case, uh, that deals with the um, Caputo and Riemann-Leibniz in both sides. So it is easy to understand you. This is the difference. I think you understand. If you can't understand what I say now, you can contact uh, me through mail or LinkedIn. I will update the correct answer. I think it is okay. Otherwise, I will repeat my answer. No problem.
Okay. Thank you, Rita. More compliments there, Tommy. Thank you for the presentation, Rita.
Thank you.
Marina Lima, congratulations and thank you, Rita. Marian, great. Marian Sultana says great. There is one more question there by Junior. Is there a generalization of the subspace methods for the Hilfer operator?
Uh, Actually, for Hilfer fractional differential operator, if we consider Hilfer fractional differential operator time, that is, I can explain using if dt delta gamma is the Hilfer fractional differential operator, which is equal to q of x w wx w dou r w by dou xr, that is q is only containing the space derivative of the dependent variable w, then to found the invariant subspace of q is same, and we have to obtain dt delta gamma ai of t equal to some combination of a's. That part is difficult for Hilfer fractional differential operator because I think Methodological E alpha 1 of x t E alpha 1 of t power gamma of Hilfer fractional derivative is Hilfer fractional derivative, and in the Hilfer book, we can obtain the solution for the d delta gamma ai of t equal to ai of t and ai of t square there, which is a generalized e Mittag-Leffler function that will coincide with the solutions of Riemann-Leibli and Caputo when the type parameter equal to 0 and 1. So obtaining the solution using Hilfer fractional differential operator using invariant subspace method. That is, invariant subspace method can be generalized to Hilfer operator also. That is possible, but uh, it is difficult to found the fractional ODE solution. A of t is difficult to found in all cases. Some known fractional ODE is solvable for Hilfer case. Uh, that's an active area of research. I am also interested in the Hilfer paper. Okay, thank you.
Thank you very much, Rita. Just a reminder that in the comment session there is a link for you can sign the attendance list in order to get your certificate.
Okay.
Pessoal, please.
Nothing.
Ok. Quem quiser, aqui é o link que está na tela, né? Para vocês preencherem a lista de presença. Gente, muito obrigada. Foi uma honra para mim apresentar esses pesquisadores tão internacionais, né? Thank you, Rita. It was an honor to me to present you. And I'm pretty sure that everybody there in this group is very happy with your participation there with us.
Thank you so much. Thank you.
Gente, por hoje é só. Até mais.